Hi everyone. It's lecture about IPv6. We will have two lecture about IPv6. First lecture is about what is IPv6 and how to use some concept features, and that's it. And the second is about IPv6 translation, tunneling, and etc. So let me begin from IPv6. So we here to share my screen. In this presentation, we will explore IPv6, the newest version of IPv Internet Protocol, which solves many problems of the limitation of IPv4. We will discuss why IPv6 is essential for the future, how its addressing system works, and the challenging we face. So IPv6 was developed by Internet Engineering Task Force, shortly IETF. It's a global organization that sets internet standards. The IPv6 introduced in 1998 to address the limitation IPv4. Since then, it has become a standard for internet communication, so its adoption has been slow. Is the Internet Protocol version 6, the latest version of the protocol that allows devices to communicate over the internet or a network. Key points what I want to highlight, what the Internet Protocol do. It's identify devices using unique addresses. It routes data packets between devices. The main reason why IPv6 was developed, it's previous protocol IPv4 uses 32-bit of addresses. This limits the number of available addresses to about 4.3 billion. With the rapid growth of internet and the Internet of Things, IPv4 addresses are not longer efficient. We have example here. The first line is IPv4 addresses 192, 168, 1, and 1. And down we have the longest IPv6 addresses, which is much longer compared to IPv4. So we will deeply explain why is that. And in IPv6 can assign unique address to every devices on Earth, including cars, sensors, phones, or even household appliances. And this is why it's critical for Internet of Things and smart devices have this IPv6 protocol. So I wanna start with the differences of the structure IPv4 and IPv6 addresses notation. So in IPv4 addresses are written using only decimal numbers from to 1 and from 0 to 9. So it means each section, for this example, IPv4 addresses called octet is decimal number between 0 to 55. Decimal numbers represented binary values of 8 bits, 1 byte in each octet. For example, the decimal number of 192 is in binary will be 11000000, so 6 zeros. Structures, so IPv4 addresses are divided into 4 octets, 1, 2, 3, 4. These octets are separated from each octet using by dot. So no letters, special characteristics, or symbols are allowed. Range of values in IPv4 has a restriction. So each octet, for example, in this case, 192, 168, can use only from 0 to 55. So meaning only numbers like 0, 127, 192, 255, and between these numbers can appear. Numbers outside of this range are invalid. For example, we cannot use 156 or higher value. So the highest value in IPv4 is this 255, the lowest value is a 0. However, in IPv6 symbols, we use it hexadecimal digits. It means from 9 to 0 and from A to F. Hexadecimal is a base of 16 number system, which means numbers from 0 to 9 are the same as in decimal, like in IPv4. But we have additional symbols like from A to F, representing A, B, C, D, E, F. So A representing 10, B representing 11, C representing 12, T representing 13, E representing 14, and F representing 15. So IPv6 addresses are divided into 8 groups of 16 bits, 2 bytes each. So this one representing one group of 2 bytes, second, third, fourth, fifth, sixth, seventh, eighth. Groups are separated by columns. If we IPv6, IPv4, we're using dots. In IPv6, we can use columns. So IPv6 allows abbreviation. Leading 0 in group can be omitted. So we will discuss it later. And the consecutive 0 groups can be replaced by double column. For example, here, if we have, here we have 0. We can just omit it and say DB8. So between 1 and 85, we can use DB8. So we know that here is a 0. If you have a consecutive zeros, for example, here fourth and second 4, we can use double columns between them. So 50, 85, 83, double columns, 8, A to E, for example. So it's representing, so double columns in this case representing consecutive 0. So it means that we have between them 8 zeros. But we can use these methods only one time for each IPv6 address. It's very critical to know. So as I mentioned, why IPv6 exhausted growth of the internet in 19th and beginning of 2000, rapid expansion of mobile devices, home networks, and enterprises, the rise of Internet of Things and smart devices like sensors, cameras, and wearables. IPv6 uses 128-bit address, which allows to 3.4 multiply for 38 zeros unique address, which is 340 indecillion IP addresses. This is enough to assign unique address to every device on Earth and even beyond. For example, if IPv4 were a postcard system where every person in city could send one letter, IPv6 like assigning every person on Earth their own galaxy to store letters. You can compare how huge number is this for IPv6. IPv6 ensures we will never run out IP address again. With trillions of addresses available, IPv6 can support the growth of the internet far into the future. Better connectivity with the end-to-end communication. IPv4 heavily relies on NAT, network address translation, to conserve address space, while NAT works at introducing complexity into networks, breaks end-to-end communication, makes certain applications like VoIP and peer-to-peer service harder to implement, creates security concerns as NAT hides devices behind a single public IP address. How IPv6 improves connectivity? IPv6 eliminates the need for NAT because it has a virtually unlimited address space, allow true end-to-end communication between devices, simplifying applications like VoIP, online gaming, and remote access, improve network performance by reducing overheat caused by NAT. Things that I'm not trying to package through the single mailbox for entire apartment building. IPv6 gives each apartment its own mailbox, making delivery faster and simpler. By removing NAT, IPv6 restores the original vision of the internet, direct communication between devices. This makes networks simpler, faster, and more efficient. However, we have barriers to IPv6 adoption. I will shortly explain them. IPv6 and IPv4 are not directly compatible. We will discuss in the next lecture. We can require dual stack or tunneling solutions. Many of the second is cost. Upgrading hardware and software to support IPv6 can be expensive. Knowledge gap is many engineers are familiar with the IPv4 and needed training to use IPv6 effectively. And the security concern, firewall and monitoring tools must be updated for IPv6 traffic, which I mentioned about upgrading hardware. And IPv6 addresses can be simplified to make them easier to read and use. We have some rules for simplification. Removes all leading zeros to each group. Like we can use this one, 2 columns here, here, here. And we can shortly use this IP address, and it is representing of this address. And we can reduce consecutive zeros, replacing with them only once per address. For example, we have all zeros, we can reduce it and use this one. But the crucial thing is do not use reducing always. You can reduce only one time. In this case, if you use it one time, you cannot use after this one or before this one. So keep in mind that the reducing IP address can be implemented only one time per IP address. Here we have IP address, we can reduce it only this part. So we can say FFE1 0, we have 8 zeros, we can shortly use A, B, C, D. But we cannot use again if you have like here some of the old zeros. So we have to write it all of them. For example, here we have to write all of them or just 1 0, but we cannot use again reduce simplify after this double time because we don't know how many hexadecimal between these values. So we will discuss about type of addresses in IPv6. So IPv6 uses 3 main type of addresses. First one is unicast. It's one-to-one communication. Example uses 2001 DB1. So it means that between 8 and 1 we have all zeros. Multicast, one-to-many communication. Example here FF02, all nodes in local network. And we have multiple receiver from other side. So we can use FF20 here. And between 2 and 1, it's all 0. Anycast, it's one to nearest communication. You use it for load balancing. Mainly, you know that Google has a lot of data centers and it uses Anycast, for example, in IPv4 addresses all 8s. So your request to google.com or Google Domain Server will be choosing only closest one. And broadcast was eliminated and is not supported in IPv6, replaced by multicast. Multicast provides a more efficient way to communicate with multiple devices. So what is the unicast address in IPv6? Unicast addresses in IPv6 are used for one-to-one communication. This means that data sent to unicast address is delivered to a single specific device. IPv6 defines several types of unicast addresses, but here we'll focus on link local and global unicast address. First is link local address. Purpose of link local address are automatically assigned to every IPv6 enable interface. These addresses are used for communication between nodes and on the same link subnet. They cannot be routed or valid only with the link local link. We have prefix, for example, FE80/0. The first 10 bits are always here 1 1 1 1 1 1 0 10. You have 7 1 0 automatically generated by operating system for every interface. Mandatory for IPv6 enabled devices, even if no other devices are assigned. So we have to use link local address, often used for network protocols such as NTP, neighbor discovery protocol, we will discuss about that, and the routing protocol exchanges. So how link local addresses are generated? The prefix is FE, for example, in our case, is assigned. The EU EUI64 format is used to generate the remaining bits from the device of MAC address. If no MAC address available, the system uses a random process to create unique identifier. About EUI64, we will discuss in future slides. Practical use cases, router-to-router communication. Routers exchange routing updates and neighbor information using link local addresses. In local device communication, devices on the same subnet use link local address for tasks like auto configuration and troubleshooting. So link local addresses are similar to private IP addresses in that they are only valid with the same subnet. Like you have branch of office. If you are using link local addresses, you cannot use these addresses to communicate as a branch of office or cities. It doesn't matter. Only inside of your local area network. Every IPv6 enabled interface must have a link local address, which is critical for local communication and network protocols like NDP. About global unicast addresses. Global unicast addresses are used for devices that communicate across the internet. These addresses are unique and routable, meaning they can send and receive data globally. Key characteristic is prefix. The first bits are here. First bits is 001. For global unicast, assigned by your internet service provider or internet organization, similar to public IPv6 addresses, the remaining address space divided into regional local subnets. So, as I mentioned, is assigned by ISP and identifies the network. For example, we have this prefix from ISP, TB8, and all 0/32. Subnet ID is 16 bits, used to create subnets. It means that after 8 we have can add 1. So the subnet IP address will be 2001 2B8 1, and all zeros between them /48, 16 bits. And so in our case, this ISP address is a global unicast address for devices. Practical use internet communication. Devices with a global unicast address can access and be accessed over the internet. If you try to use after these numbers UE64, so you can be routed outside of your network. Business a global unicast address to connect branch office, cloud servers, external office. To connect to many of branch office, you can use global unicast address, which can assign from your ISP. In our case, this value. So if you use the EUI64, you can route each devices because we have so many IP addresses in our network. So global unicast addresses are likely public IPv4 addresses, allowing device to communicate across internet. They are assigned by ISP and structured to make routing more efficient, supporting billion devices globally. So here is multicast addresses. In IPv6, broadcast is used to send data to all devices with specific network. If we have like one network, we have bunch of devices, for example, 1,000 devices. It broadcasts, if one device is broadcasting, so it sends packet to all of them. And while it can be useful, broadcast creates unnecessary traffic because it sends data to every device, even they don't need it. So why we replace broadcast with the multicast? IPv6 replaces broadcast with multicast to make communication more efficient. Multicast sends data only to devices that are part of specific group. So, for example, if you have a in your network many of devices, we sending packet only specific devices. So we don't need an IPv in IPv6 broadcasting. It reduces network traffic by avoiding unnecessary transmission. Multicast is more secure because data is not sent unattended device. Multicast allows one-to-many communication where data is sent to group devices instead of all devices network. In IPv6, multicast addresses start with the prefix FF0. For example, here 00/8. FF identifies the address of multicast. Here, all zeros is defines the scope where the multicast traffic is valid. We have some of scopes of multicast traffic. IPv6 multicast traffic has specific scopes defined by fourth digit FF01, internet local, only for local devices. FF02, link local, valid with the local network segment. FF05, site global. It's site local, valid with the organization, and we have as well 0F0E is global, so we can use for all of the internet. So here example FF02, all nodes on local network, FF02, all zeros to all routers and local network, and the 5 here is OSPF v3 routers. It means OSPF in IPv6. OSPF do not, it doesn't mean that it's part of OSPF which we are using in IPv4. So we have some of the future IPv6 in security. One of the most significant improvements in IPv6 is on security. Unlike IPv4, IPv6 was designed with security in mind from the very beginning. Its built-in features like IPsec provides better protection for data and reduce vulnerabilities. So IPsec is suite of protocols that provide security for the internet communication by encrypting authentication data packets. Key features of IPsec and IPv6. Encryption ensures that data is secure and cannot be read by unauthorized parties during transmission. Authentication confirms that data comes from the trusted source, and the integrity verifies that data has not been tampered with it during transmission. How IPsec is built into IPv6. In IPv6, IPsec is mandatory for all devices. That means that any devices of IPv6 enabled system can use IPsec for secure communication. IPv6 ensures compatibility with IPsec, simplifying the process of setting up secure connection. Example use case: a company uses IPsec with IPv6 to securely connect remote office over the internet, ensuring that sensitive information remains private. End-to-end encryption protects the transmission. It means encryption is core feature of IPsec, so ensures that it remains confidential during transmission. If the attacker intercepts the packet, they cannot read the contents of your packet, so it will be encrypted and they cannot see the content of your packet without encryption key. How IPv6 enables end-to-end encryption. IPv6 eliminates the need of network address translation NAT, so we don't need a NAT in IPv6, which often breaks encryption in IPv6 networks. Without NAT, IPv6 can maintain encryption from the source to destination without requiring additional configuration. So practical benefits of this secures communication for all applications like VoIP, video conference, and online banking, protects data for in transmitting for service like remote access, VPN, or cloud application. So end-to-end encryption in IPv6 ensures that sensitive information like login credential or financial data remains secure from the source to destination. This is especially important for business handling private users. So next is NDP. So what is the NDP? NDP, Neighbor Discovery Protocol, is a critical component of IPv6. It replaced several IPv network functions, including ARP, Addressing Resolution Protocol, ICMP router discovery, and parts of DHCP. NDP operates using ICMP v6 Internet Control Message Protocol for IPv6 and handle tasks that are essential for device communication on IPv6 network. Why we had to replace ARP with NDP. In IPv4, ARP uses broadcast messages. So as I mentioned, in IPv6, we do not use broadcast message. We can flood the network and reduce efficiency. IPv6 eliminates broadcast entirely, so replacing with a multicast and unicast communication through the NDP. NDP provides more advanced functionality compared to ARP. Neighbor discovery replies in ARP and IPv6, enabling devices to find and communicate with other devices of the same subnet. I will discuss about function of NDP. Router discovery allows device to locate routers on the network automatically. This is critical for devices to know where to send traffic destined for other networks. So devices first connect and device in IPv6 device send router solicitation RS messages to multicast address. For example, is FF02. Router responds with the router advertisement message containing the network prefix, default gateway information, other network configuration like domain name, service, and it's compared to reach the default gateway and what kind of network prefixes are used in your local or global network. When your device connect to internet, so when you first time connect device to your network, so it sends RS to discover nearest routes. The router responds to him array message router, and device configured its IPv addressing using CLASLAAC. So benefits of router discovery is eliminate the need for manual configuration for default gateways, enable dynamic network configuration. So NDP simplifies the process of discovering routers. Instead of manually setting the default gateway, devices uses RCs and advertising message to find nearest router and configuration themselves. So the next is IPv addressing conventions. What is the CDR? CDR is classless interdomain routing. Notation is a compact way to represent IPv address and its associated subnet mask. It's widely used in both in IPv4 and IPv6 for efficient address allocation and routing. For example, in IPv4, for example, for we can use between two devices /20. We can say do not specify address. It means that we have 4 IP address in our network, or /22 when you have to assign loopback. In IPv6, CDR notation is particularly important because of the largest address spaces. It simplifies address management and enables flexible subnetting. So we can, in IPv6, we can use, oops. So we have standard in IPv6. The network prefix /64 identifies the subnet. The prefix length, the number after the slash. We have, like, for example, 64, 63, 62, or until 48. It specifies the number of bits used for network portion of the address. We have example here, like /64. The first values of this one is the prefix, network prefix. The first 64 bits are reserved for the network, while the remaining 64 are used for device address with a subnet. We know that IPv6 address is created 8 hexadecimals. /64, it means that we can use this of our IPv6 address for device addressing in our subnet. So this prefix, the first half of prefix 64, is used for identifies our network, and the second part 64 is for assigning devices. EUI64 in our subnet, it means each device is often generates the IPv6 addressing using EU64 format. We will discuss a little bit later. Simplicity, using 64 prefixes ensure consistent subnet size across network, making them easier to manage. Scalability, /64 subnet can support 18 quintillion unique devices. It means like 2 64 zeros up to 2. For example, we received this address for my ISP. So it means this range of reserved for us from ISP. We can use the second digit of this value, or 1, for example, for IT department. Second value of this network, for example, for HR department, and etc. 3, 4, and but we have to use this value as a ISP provider subnet. So, however, this is 64, this is 64, this is /64. While 64 is a standard, smaller subnets are used in specific cases, which I mentioned. We can assign single IP address. We can use /128, for example, for our loopback. Use it for point-to-point links or loopback addresses. We can use /127, often use it for point-to-point links between routers when we have a couple of routers. /48, use it by ISP to allocate prefixes to customers, allowing each customer to create multiple of /64. So, for example, of between router connectivity, we can say that 2001 DB8 between these ones, all zeros, and /127 and 27. We don't need to use a mask in IPv6, so we can just simplify the IP addresses Sign this. So we can simplify IP addresses, only assign CDR notation for subnetting. So IP addresses can be long and complex, but there are rules to make them readable, which I mentioned before. We can remove leading zeros, replacing consecutive groups of zeros with these symbols, and replace double column. Like between these 1 and 2, we have all zeros. But you can only use double column on an address to avoid ambiguity. I can give another example. 2001 0GB 8, all zeros. We can simplify the address like this, 2001. And we can just exclude this zero, so it means DB8, double column. Can reduce all these zeros by showing only zero. So one. So the next is EUI64. It is a method used in IPv6 to automatically generate a unique interface identifier. So last 64 bits of IP addresses, for example, or if we have the first half of 2128 is 64 bits getting from ISP, we can use device MAC address as a foundation to ensure the identifier is unique. UE64 is commonly used stateless address after configuration, shortly CLAS, allowing devices to generate the IP address automatically without needing a DHCP server. So we have a couple of steps. Process for converting 48. So in MAC address has 48 bits. But we have to make it 64 bits. Interface identifier using EUI64. First, we have to divide it, the MAC address, two halves. So first half is, we have, for example, 1001122. It is 48 bits. We have to divide it. So the first half is 001122. Second half is 334455. So we are inserting FFE between two halves. So we have 001122. So we are inserting FF, FE, 334455. But we have to invert the seventh bit of the first byte. The seventh bit of the first byte is flipped to distinguish between global unique and local administrated address. If the bit is 0, it indicates global unique address. If the bit is 1, it indicates to local administrated address. So converting the first byte from hexadecimal to binary, original is 00, binary is all 0, inverting fourth bit, the second bit from the left. So final result of flipping process will be 0, 2, 1, 1. 22, 32, 44. So we have unique IPv6 address. We can use prefix for this address. For example, here will be 2001 DB 8 all zeros. This is the address of our global unique address and ensures the device can communicate on the network without complex. Why we have to use EUI64 automation eliminates the need for manual configuration of IP addresses, simplifies network management in large deployments. By using MAC address as the base, EUI64 ensures unique IP address identifiers across all of the network. So works with this after configuration, allowing device to generate their own IPv6 addresses, but we have limitation. So privacy concern, because the MAC address is embedded in IPv6 address, it could expose all a device hardware details and make it traceable across networks. So in this case, we are flipping here. This one, we can identify what kind of MAC address is used in specific network devices. IPv6 provide temporary address and privacy extension to addresses concerned by generating random interface identifiers instead of using EUI64. A real-world example for this is enterprise networks device automatically configuring the IP addresses using EUI64, reducing the administrative workload, and the Internet of Things, IoT sensors and smart devices often uses this method to ensure unique address in large-scale deployments. Stateless and stateful DHCP. In stateless DHCP, devices configure their own IP address automatically without the help a DHCP server for address assignment. Instead, the device uses router advertisement message sent by router and the stateless address configuration mechanism. So how stateless DHCP64 works, it's router sends array, router advertisement, so with the flag 1, indicating that additional configuration is available for DHCP server. Devices generate the IPv6 address using CLAC combines advertisement prefix and the EUI interface identifier. The device contact a DHCP server only for additional settings like domain name server, domain server name, and search domain names. What is the advantage of using stateless DHCP? No need a central DHCP server to manage IP address allocation, reduces administrative overhead. Devices can configure themselves automatically as soon as they receive router advertisement. For example, a laptop receives prefix from the router. It's like 2001 DB 8 0/64 and generate unique address, which we did in EU64. It queries a DHCP server for domain name servers of Google. We are ready to use this device into the internet. But other option is stateful DHCP. So router set M flag instead of 0 flag. Router sends array with the M flag. 1 indicating the device should use DHCP server for address configuration. It means that device cannot automatically assign their own IP addresses. So each time device requests IPv6 addresses and configuring details from only DHCP server. The DHCP server assign IP addresses at least time on other network setting like domain name servers. Advantage of DHCP server provides centralized control for IPv6 address allocation. useful for enterprise networks where administration need to manage IPv leases and track devices, ensures no duplicate IP addresses, as all assignments are handled by the server. Example, a printer connects to the network and sends to DHCP 6 request. The DHCP server assign address of specific 2001 DB100 in the end, for example, and will release time with release time 7 days. Oops, days. And adding the domain name servers. I think for this lecture, that's it. In the next lecture, we will discuss tunneling, IPv4, IPv6 communication, etc. So for this lecture,